So this is a work made by Hussein Nassar during his postdoc last year, and it is a collaboration between Hussein, Laurent Monaz from Cermix, which is a math laboratory at École Nationale des Ponts et Chaussées, and myself at Laboratoire Navier. And the idea is pretty simple. And it's a long time ago I was interested in this this question. Is that I'm doing origami, okay? And there are very famous origami tessellations. This one is very, very famous, and if you look in, there are many papers regarding metamaterials in doing mixing origami and metamaterials. And since I'm a child, I know that I can achieve some fancy surfaces with this kind of origami. Okay, I can bend it, I can stretch it, and I can chalk it somehow. Okay, and the starting point is that of the equation is that originally this is paper, so it is meant to be developable. Okay, I will be more precise about that. And now this is still developable, but with some regular corrugation, and I can achieve average surfaces which are not developable. That's the starting point. So this is Miura Ori, which is very famous. There are other origami tessellations, and I will talk about the eggbox pattern today. And this other one is rather famous, and it was investigated by Tashi and Leo. So that's the starting point. It is a form-finding problem. What are the motivations? So I'm from a civil engineering lab. So I'm doing generalized continua. I don't know why, but okay. And in civil engineering, we want to design structures. Okay? And it is very trendy to design fancy architecture with fancy geometry, which is very expensive to fabricate. Okay? So the idea here is that since you have a regular pattern which is behind, you might expect to spare some money because you have a repetitive element, but you can achieve some kind of free form, but it is not free. Okay? Or less regular than purely developable shapes. Okay? So this is the first motivation, which is freeform architecture. And currently most approaches are based on variation of the pattern. Like Giuseppe was suggesting for the clocking device, you can vary progressively the microstructure in order to tune its property. But the point is that you drop the idea of the repetitive element. You make vary the element, so it is not very interesting. So what I'm interested in the architecture geometry is, can you still keep true geometry? The second motivation is more related to generalized continua. What would I do if I want to upscale the behavior of this thing? Okay. If I assume finite elastic contrast, meaning everything is a single body with this corrugation. Okay, I expect that I will have a shape without self-stress. Okay, and then I will, if it's flat, I can perform periodic plate homogenization. Okay, and I need to assume small strains. All right. And this is a framework which is quite well established. The point is that I'm still limited to small strains. If I go in large strains, I get into troubles. I need to use block waves for buckling or whatever. Okay, so it's very difficult to tackle. Yeah. I just want to first simplify my problem, and then I will go in. Anyway, it is quite difficult to tackle in this using elasticity. So my idea is that if I go to infinite contrast, so it's pure geometry. So the idea is now I mean the framework is more about pure geometry. I have some links, and I want to satisfy these geometrical constraints on the periodic pattern. And in that case, I think we can go in large strains. And the point is that I want to find the geometry I can achieve with this pattern, with this assumption. So these are the motivation. So I will just recall some historical examples of fitting problems, because there are other ones, and it is interesting to recall them. And I will study the case of the eggbox pattern, which is not exactly an origami. And then I will show some illustration of fitted surfaces, simple cases. So the first fitting problem found in the literature is quite early, it's from earlier. And it's just what can you achieve with a sheet of paper without folding it. It is well known that you can achieve developable surfaces. And the reasoning is that paper, you assume that it is unstretchable in its plane and it is fully flexible. And then it means that the Gaussian curvature is 0, and from theorem equation from Gauss, you know that you can achieve developable surfaces only. And it is remarkable that you have a local constraint on the curvature and you get a global property of the surface. Okay? And you have three types of developable surfaces: cones, cylinders, and tangent developable surfaces. This is the first case. But as I said, if I fold it regularly, I can achieve more general surface. And there is a very famous historical anecdote about Lebée and the Lebée handkerchief, who, comment dit français, wrinkled a handkerchief and say, hey, this is still developable, but I can achieve whatever surface I want. So it goes to another question, interesting question about Nash. Okay. The second, and this will interest many people, and especially Francesco here, is the Chebyshev nets and grid shells. So if I have a collection of wires which are regularly spaced and with spherical joints at the intersection, it's like a pantographic lattice, but without bending energy in the wires. So it's if I do that, I can transform the shape and achieve a double curvature shape. And when I add a third direction of bracing, I can achieve such a structure. So this was done at Laboratoire Navier. It's about 15 years we are working on grid shells. Okay, and this is this is a lattice of flexible rods which are connected together. And this was built for Solidays in 2012 or 11, I don't remember exactly. And in this case, the fitting problem ends up to find Chebyshev parametrization of a surface, which means that you have a given surfaces, and you want to find a parametrization such that the metric has the following form, and the curvature is free, where phi is the angle between the wires. Okay. And historically, the first one who investigated is Chebyshev, and it was for clothing. Okay. Now, what about origami? Origami tessellation. The first occurrence of the fitting problem for an origami tessellation was actually they struggled with that, but they didn't find, they haven't been further. Was tackled by Ron Resch and Hans Christiansen in the 70s. And Ron Resch designed this very nice pattern, which has very nice properties. You can achieve very beautiful shapes, which is it is an origami tessellation. And they wanted to build the largest Easter egg. So it is purposely, I don't know why, but the largest Easter egg in the world. And in Vegreville in Canada, it's a small Ukrainian community, and they are very. It is very important for them for Easter is very important event for them, and they wanted to make this shape from this pattern. And as reported by Blin, they spent 6 months trying to fit this shape, and they couldn't. It was impossible. So I find it, I mean, they haven't been further, but I think it's interesting. And what they did, if you look here, there is a remnant of this pattern, but they dropped the foldability. It's not an origami anymore. Now, what about origami tessellation? More recently, you have most interest is driven on murari, which is here, and the eggbox pattern. So it turns out that if you stretch murari in its plane, you can its planes in the other direction, so it has a in-plane negative Poisson's coefficient. Okay, and if you bend it, in one direction, the opposite curvature, the transverse curvature is in the opposite direction. So it is a positive out-of-plane Poisson coefficient. Okay, it is a matter of definition. And this was proved in rather recent papers. And I will be more interested in another one, which is the eggbox pattern. And this one is also flat foldable. And if I stretch it, you see that the Poisson's coefficient, the in-plane Poisson's coefficient is positive. It is a classical behavior. And if I bend it, I can achieve double positive curvature, which means that the out-of-plane Poisson coefficient is negative. Okay? And this was achieved considering one unit cell and perturbating the unit cell. So it is only in small strains. So the purpose of the talk is to address the eggbox pattern, but allowing large strains. So what is the eggbox pattern? Actually, it's not an origami. It is not developable. It's a collection of pyramids with alternating the tip. Okay, and on this drawing, all edges, back edges, are considered as hinges. They are joints. Okay, so these parallelograms are not expected to remain flat. Okay, if you force them to remain flat, there is only one double degree of freedom of motion. So I need to allow these parallelograms not to remain flat; they will fold. Okay. Okay, it is not developable, it is not an origami, but it still complies with rigid folding rules. Okay? I mean, each vertex is a spherical joint. So this is the eggbox pattern, and if I want to, I need an explicit construction of of its geometry, and so I will investigate first a single pyramid. So a single pyramid is actually completely driven by a single degree of freedom. And I will introduce the folding angle, this red angle, and all the other parameters are set. I mean, the other parameter is the dual folding angle, and it is completely related to to theta, the folding angle, okay? Because there is a single degree of freedom. And it is a rigid folding motion, meaning that the face, if you assume that they remain flat, there is a single degree of freedom. So R will be the size of one edge of the pyramid, and here the triangles are equilateral, but it doesn't matter. And the last point is that if I know A, B, and D, I can construct E, because it is the intersection of two spheres, and then I can construct C. So knowing A, B, and D sets the whole pyramid. It's pretty simple. But if from this observation, I have a direct construction procedure of the eggbox pattern. And as follows, I consider first this zigzag line, the blue line, which is a diagonal line. Okay, and I can propagate the information from another line, and then from the other one, etc., etc. But you have a narrower domain, like a hyperbolic equation. Okay? So if I do this for zigzag which is confined in a plane, I get this square. And if the zigzag line is on a circle, I get this kind of surfaces. Okay? Now, the diameter of the circle is 1. And if the size of the pyramid is 1/4, I get this rather coarse surface. Here you have the whole pattern. Here I show only the mid surface, so that it is easier to see, to capture. So I start with this size of the pyramid, and I get a smaller and smaller pyramid, and it seems that it converges to a limit surface. Okay, so this is an empirical experiment. It is empirical, and I would like to generalize this idea. So, how I can do that? I'm doing a kind of two-scale expansion, but it is formal. So I can extract a unit cell, okay, which is the purple domain here. I define a reference vertex, And all the red vertices are the reference vertices. And of course, the typical size of the unit cell is R. And I want, with proper scalings, I assume R is going to 0. So if I want a smooth parametrization, I need to know, I need to define kind of tangent from the tangent plane and the curvature. So how I can get that? I can compute the finite differences between reference vertices. And the first rank finite difference will define the first fundamental form, and the second rank finite difference will define the curvature or second form tensor. One key point is that if it is meant to be smooth, those finite difference has to be independent from the point I am considering, since it is meant to be homogeneous and continuous. Okay? So locally it has to be independent of the position of the unit cell I am considering. And if I do that, which I will detail a bit later, I will find some constraints on the metric and the curvature of the limit surface of the continuous, the equivalent continuous surface. So if I do that for the metric, which is the first fundamental form, I can compute the finite difference in two directions of the reference vertices, and they have to go to a limit, and which is independent of the local index, and this defines a tangent plane. Okay, so I don't give more details here, but what is really important to notice is that it means that the pattern has to be locally planar. Okay, so you need to have a periodic state which is planar. Okay, this is planar, this is not planar. So it needs to be at leading order locally planar. Okay, and it turns out that for the eggbox pattern, you have a collection of planar configuration from one flat-folded configuration. Okay, and I can expand in the other direction. Still, the overall pattern remaining flat. I will show you an animation later on, or maybe I can go. Maybe it is at the end. This is that. Okay. This is the flat folding motion. It is still all those configurations are on average planar, and they are parameterized by the folding angle. Okay. So you have a continuum of collection of possible tangent plane. That's the first point. And then from I can do this for make this explicit for the eggbox pattern. I find that the metric has the following form, and from the metric I can compute the in-plane Poisson's coefficient. For instance, it turns out that it is the exact opposite of the Miura-Ori Poisson's in-plane Poisson's coefficient. That's another important feature is that it is really important to have this collection of planar periodic states. Otherwise, the metric is completely set, and so you cannot achieve double curvature, because it becomes at best developable, since the metric is set. So this is for the metric. Since the eggbox pattern has several metrics, I can look at the curvature, the second fundamental form. Okay. Here it is the same procedure, but I need to perturbate this planar configuration. So I need to perform an expansion with respect to the small parameter. I don't give details here. And in the end, this is the form of the second fundamental form, where you still have the folding angle and its dual, the dual folding angle, and n and m are unknown functions of the curvilinear coordinates. Okay. From the second fundamental form, you can compute the ratio of the curvature radii, and compute the out-of-plane bending, Poisson's coefficient. And it turns out that it is positive. It is exactly the opposite of the in-plane coefficient, And it is also the opposite of the Mura-Horry Poisson's coefficient. It is, these both patterns are very, very closely connected. So we have everything for formulating the fitting problem now. And basically it consists in finding a parameterization of the surface such that the folding angle on two unknown functions yields such first and second fundamental form. And for doing that, these functions has to comply with the Gauss-Kodadzee-Menardi compatibility equation. So there are three equations. It turns out that a necessary condition is this vectorial hyperbolic nonlinear partial derivative equation. Okay? It is a necessary condition, but it is not sufficient. But it reveals it is the continuous it is the if you remember, I presented a procedure to construct directly the eggbox pattern from a single diagonal, and this is the continuous equivalence equation. And the last point is that any local fitting is possible. You can fit any curvature, but in the limit you cannot have equal radii of curvatures. You cannot fit a portion of sphere. But it is a limit result, and in such case it has to remain found. So this is for local fittings in a small neighborhood of the surface. Now, if you want to investigate global fittings, you need to solve those nasty equations, which are nonlinear partial derivative equations. So what we do in this case, we remove one or two coordinates, and we try to find closed form solutions. This is what did Hussein very brilliantly and efficiently, and I will show you some results. If you assume that the first and second fundamental form are uniform, if the first fundamental form is a uniform, it means that it is developable. And if the second fundamental form is, if it is uniform, it means that you have a cylinder. The radii of curvature are constant. And this is, in this case, it defines a single, you have a single family, you have a single parameter family of surfaces, and I will show you the animation, it will be clear. So I have a single cylinder. This is, you have this single cylinder. This is the same motion with two different views. So you see the radius of the cylinder is the same, and I'm just varying the folding angle. And you have the collection of the whole possible fittings over a cylinder. Okay. Now, if I investigate axisymmetric surfaces, it means that I'm dropping only one coordinate and I'm keeping the other one. I have again a single parameter family of surfaces, which is as follows. I will show you the animation. And all these surfaces, the axis of axisymmetry is this, in this direction, and here it is out of the plane. Here it is out of the plane, and here it is in the plane in the horizontal direction. And in all these surfaces, you can see here the radius, the largest line, the radius of curvature is constant. Here. Okay? We are fitting a kind of circle, and you get this axisymmetric fit. Now, the last kind of surfaces you can easily obtain with this pattern is that you can almost flat fold it, okay? And then it behaves like an accordion. So you can achieve ruled surfaces, okay? So we formally, we've been a bit further, doing the correct expansion, and define a procedure to build these ruled surfaces. And what you can see here, the gray surface is an hyperboloid of revolution, and it is the target surface. And this is the blue surface, is the mid surface of the eggbox. And you can see that when it is almost flat folded, the fitting is pretty good. But as soon as the pyramids are quite open, the fitting is not so good. But if you go in the limit and almost fold the pattern, you will fit as far as you want. So this closes my presentation. So in conclusion, I think it was interesting to have purely geometric consideration to find those surfaces. What is important is that we achieve strictly periodic fittings, which is from this limit process. And here, as you have seen, we allow large strain of the unit cell. What would be interesting is to investigate is the mechanical behavior of such microstructure. And as Pierre mentioned yesterday, discussing with Pierre, Hussein, and I, we realized that you can achieve some generalized continua with this kind of patterns. And another interesting question is what happens when the unit cell is not so small. It is like in generalized continua in general, but even with pure geometry, we realized that we are not able to achieve surface in the limit process which are achievable when the pattern has a finite size. So the freedom is a bit, you have more freedom here with a finite size than what can be achieved in the limits, when the unit cell is very small. And to conclude, this work was published in the Proceeding of the Royal Society and was funded by Labee's M&MoCS, which is part of the Investissement du Futur. So I would like to thank you for your Thank you.
Any questions?
I don't know why you made this assumption to small deformations. All your examples were large deformations.
Yeah, I just meant that if I want to deal for the motivation, it's just that it was just for motivation. If I do finite and with elasticity, not geometry, finding the large transformation of this pattern and the homogenized behavior of this microstructure is not so simple because, for instance, you might have some buckling, local buckling, and this is very difficult to understand the mathematical formulation of this when you're dealing with finite elasticity. And the point of doing pure geometry is that it becomes completely discrete when you do finite differences. And then we allow the unit set to have large strength.
So what is the final aim? Do you want to model it as an elastic plate or an elastic shell or what?
The final motivation is first it is obvious that even without elasticity the surfaces are not trivial.
That's right, yeah.
And I think it is fair enough to first investigate in pure geometry what you can achieve on average, because anyway in the limit behavior of elasticity for very thin membrane, if it is very thin and it complies with the assumption, these kind of assumptions, you know that in the limit it has to fit such surfaces. So it is good to know what would be the limits of elasticity when you a priori assume that the contrast is infinite, meaning that it is pure geometry. That's the point. It's kind of the same idea for Chebyshev's nets. I mean, you can investigate pantographic structures, but we know that at leading order, it will behave as wires, and it is, and we know that the achievable shapes will have to comply somehow with Chebyshev parametrization, and then you can add elasticity in that framework. Mm-hmm. But later on, it is the limits behavior will be this parametrization. If you want to achieve large strain is a bit improper, but large displacement of such magnitude.
Displacement and rotation, sure, yeah.
Mm-hmm. You mentioned at the beginning, you said that this is a fault finding problem.
Yes.
Actually, it's not the classical fault finding because there you have equilibrium, you have only geometric constraints here.
Yeah.
And so the and the parameter you impose probably is in this case the angle. So do you know if there are any way of getting some theorems that allows you to find all kind of available forms?
Depends.
Or anybody has given some hint?
If it's a conformal mapping, you can achieve whatever shapes. Here it's not a conformal mapping, it is very complicated. And this fitting problem is very difficult. It is nonlinear partial differential equation, and it is not obvious what you can achieve with this microstructure. With other patterns, for instance, Hussein did all the job for mirroring, and it is very interesting either. It is you can achieve different surfaces. So it is each time it depends on the microstructure. So I mentioned that it is a form finding problem from the point of view of the architect, where you have a given shape and you want to know if it is possible to achieve it with such microstructure. But it is not what we would do. We are doing generalized continua and homogenization, and we just want to know what is the limit behavior. But for the architect, it is a difficult problem to tackle. For instance, we had a PhD at Laboratoire Navier on ceramics about Chebyshev net. It is a very difficult mathematical problem to solve. If I give you this surface and you want to find the optimal way to put a Chebyshev net on this surface, it is a very difficult problem to tackle.
You said something interesting. If your cell size is getting smaller and smaller, you go to the limit, then the formation or character of the geometry is changing. Is this maybe because of the thickness of your structure with respect to the height of your pyramid is changing? Or in this idealization of making your cells smaller, are you also automatically making it thinner?
I have no answer to that. It is a very difficult, but we are all dealing here trying to capture the size effects or the boundary effects on whatever. But here, the equation you have in the end are nonlinear partial differential equation, which is even more difficult than when you are doing linear elasticity and homogenization. And
But in the whole consideration, is the thickness important or not? Because you have a sheet and you start folding, and in the end you have a structure with the pyramids of the height. Is it important how thick your initial sheet is, or is it not important?
Obviously, in the limit process, the thickness of the pattern vanishes, because you want it to have as small as possible.
Not the pattern, the sheet that you are folding.
Oh no.
Not the pyramid size. I mean the sheet itself.
Here, since you are devising about pure geometry, the correct physical model is this one.
Yeah.
The truss.
Okay. You don't have to.
I have two practical questions.
Yes.
It works well with paper, but without what kind of material you can do it so efficiently? That's the first. And can you do it from an industrial point of view easily or not?
It turns out that all this story began because I found a way to fabricate this with metal aluminum sheets.
Okay.
And I dropped it because the application, the market was not ready and so on. It's a long story. And also because...
So this means that with aluminum sheet you can still have the large level of deformation without breaking? Or?
It is the whole trick is to find to drive the buckling pattern.
Okay.
So you give the starting point of the buckling pattern, and then once you've given that, you can fold it.
Okay.
Because you know that buckling of plates, you have as many. It's a long explanation of the number of buckling shapes you can, buckling modes you have, especially if it's infinite, if the shape is infinite. This is the first question.
Really?
And there are people who are making it with from Kevlar, carbon fibers, and on metal sheets.
And last, maybe you can make expansion, a classical test of expansion. It not works because you have the curvature. Or not? Can you have a simple modulus?
It doesn't seem obvious, but I can stretch it without bending it. It is uncoupled because it has sufficient symmetry so that you can stretch it in its plane without bending it.
Okay.
And actually, it is. I haven't mentioned that, but here, if you have this coupling between stretching and curvature, giving curvature, you cannot do this homogenization process. Why? Because you stretch it, it curves.
Okay.
And since it curves, and when you go to the limit, this curvature goes to 0. So you have a point. And it is a really tricky.
Do we have another question?
But I have only one, not three. I guess you can have a locking phenomenon depending on the ratio of the thickness of the sheet if you view it as a shell to the radius of curvature, I guess.
In the procedure I described not because I'm doing devising only geometry, but yes, indeed you have those laws.
You want to go to more extreme large trains probably to get it out of plane.
Yeah, but this locking phenomenon would deal with the contrast between the bending energy and the membrane energy. But since you have facets here, they are all locally almost planar. So I guess it will be a problem. It wouldn't be a problem. But we can discuss that further.
Last question.
There is a zero boson coefficient in the upper end extension of that.
No, both. This one has a positive in-plane Poisson's ratio, and this one has a negative Poisson's ratio in its plane. Okay. Otherwise,
you can play with zero boson.
Sorry?
You can change the geometry and have zero boson.
For this one?
I mean, some
Changing the geometry.
I don't think so.
No?
No, it would be a limit case. No, I don't think so. I think it's not possible.
With several methods.
No, not except the yeah, we can discuss that. I don't think so.
Compositor for multi-layer complètement compatible. Okay, so no more questions. So we are closing the session for today.